here. Okay. Okay. So it's a great pleasure to welcome Rachel Somerville as our fourth Quid Ultra colloquium speaker for 2022. Rachel is a great expert on galaxy formation and evolution. She has been interested, and she has been investigating how galaxies and supermassive black holes form and evolve within a cosmological context. And she started this many years ago by developing one which is still one of the most extensively used semi-analytical model, the Santa Cruz model. She did that for her PhD that she got in at the University of California, Santa Cruz. But then she moved around and changed several different institutes. She went for postdoctoral positions at the Hebrew University of Jerusalem, and then at Cambridge, and then she held faculty positions at the University of Michigan and Johns Hopkins, and was on the research staff of the Space Telescope Science Institute. She then moved again to Europe, where she was a group leader at the Max Planck Institute for Astronomy in Heidelberg. And she held the George and Margaret Downsbrough Chair in Astrophysics at Rutgers University. And currently, she's group leader at the Center for Computational Astrophysics at the Flatiron Institute in New York. She was awarded the 2013 Danny Heinemann Prize for Astrophysics by the American Institute of Physics, and a 2014 Simons Investigator Award by the Simons Foundation. She has been, working on many different aspects of both the galaxy and supermassive black hole formation, including extensive comparison with observational data. And she's also within the early release science team chairs of the James Webb Space Telescope. So we are really looking forward to this data and how she will exploit this in the coming months. So I now leave the floor to her and listen to what she will tell us about how to develop new galaxy formation models that will help us learn the universe. Thank you, Rachel.
Thank you so much, Rafaela, for that very kind introduction. And thank you for inviting me to be with you virtually today and share some of our recent work with you. I just want to check that everyone hears me well on Zoom and there in that room. Yes?
Yeah.
All good, wonderful. So before I start, I'd also like to thank my collaborators. This is work that's been done by many people working together. And on individual slides, you'll see some of the names of the people from these teams that have made this work possible. So we think that the universe began with very simple initial conditions. A Gaussian density fluctuation spectrum produced by these quantum fluctuations that were ripped apart during the epoch of inflation between around 10 to the minus 36 and 10 to the minus 32 seconds after the Big Bang, and that those density fluctuations were processed by gravity and amplified by gravitational instabilities to grow into the structures that we see today. But the big mystery, perhaps, is how we get from those very simple initial conditions, which of course we can probe very accurately with observations of the cosmic microwave background, to the complexity of the galaxies and the large scale structures that we see in today's universe. So this is kind of the big question that we're working towards understanding better. Of course, we have this standard picture that we call the lambda CDM picture, in which the universe is dominated by dark energy and dark matter. But there are many questions even still connected to this paradigm. So is inflation really right? There are many details about the inflationary paradigm that still remain unclear. What were the initial conditions of the universe in detail? And then, of course, the really big questions, right? What is this mysterious but critical dark matter? And what is this even more mysterious dark energy? But one of the main successes of this paradigm, as I'm sure most of you are aware, is that if we take those initial conditions from the cosmic microwave background observations, we put it into a computer, we let gravity do its work, that the large scale structures that are produced, seen on the right here from a simulation that contains only dark matter, the Bolshoi simulation, those structures look very similar to the ones that we see on the left from galaxy surveys like the Sloan Digital Sky Survey. So the Lambda CDM picture is very successful at reproducing observed structures on large scales, scales of a few tens of megaparsecs and larger. But of course, we know that the galaxy population is incredibly rich and diverse. We see many different types of galaxies. Each of these galaxies is unique and special, but these galaxies have correlations between their internal properties, so properties like their masses and their colors, and their large scale environment. So on the right, you see again, distribution of galaxies from the Sloan Digital Sky Survey. So here, each of these dots is a galaxy, and it's color coded by the actual color of the stars in the galaxy. So we know that, for example, red galaxies or massive galaxies cluster much more strongly than disk dominated or blue galaxies. And in addition, again, although galaxies are very complicated and every galaxy is unique, they obey these, in some cases, very tight scaling relations. So there are many famous examples. For example, the correlation between a galaxy's bulge mass and the black hole mass seems to be very, very tight. There's almost no room for any intrinsic scatter. And there are many of these scaling relations. So stellar mass versus star formation rate, stellar mass versus galaxy size. There's a connection between the halo mass and the stellar mass of the galaxy that also seems to be quite tight. And many of these relationships, so we're seeing here two-dimensional projections of these scaling relations, but we know that many of these are actually sort of manifolds in a higher dimensional space. So these are sometimes called fundamental plane relations in 3 dimensions, but these may actually exist in a much higher dimensional space. And that manifold, that high dimensional manifold, is presumably encoding some very critical information about the physics of how galaxies formed and what shaped these observable properties. So we also know that certainly within this Lambda CDM paradigm, that what we call feedback from stars and supernovae and accreting black holes is absolutely critical for producing galaxies that obey observed properties. So for example, here again is this relationship between the stellar mass of the galaxy, here normalized by the total mass of baryons in its halo. So if you imagine a galaxy living in a big dark matter halo like this, this denominator is just taking the universal baryon fraction times the mass of the halo, and then the mass of the halo on the x-axis. So what you notice, and all these colored lines are empirical constraints on this relationship, is that galaxies are very bad at converting baryons into stars. So this ratio, even at its peak around the mass of the Milky Way, is only about 20%. And at lower masses and at higher masses, it's only a few percent. So something is preventing baryons from cooling and turning into stars. We also know that if we don't include or don't properly include these feedback processes, that we cannot produce galaxies in simulations with structures that resemble those of real galaxies. In particular, it's very difficult to make disk-dominated galaxies. And this is something that the community struggled with for decades to figure out how to produce disk-dominated galaxies in this Lambda CDM paradigm. So let's dig in a little bit to these feedback processes. Again, this is sort of a word that gets thrown around, but let's think about what is really happening physically. So as we've already discussed, as the universe expands on large scales, the density perturbations seeded by inflation grow and form this cosmic web of filaments that you see in the background here in the red and black. And of course, the gas also feels the same gravity and accretes along these filaments into dark matter halos, where it can shock, but then cool. And eventually it cools enough, becomes dense enough that it can form stars. And then as stars begin to shine, massive stars can affect the gas around them through radiation, and eventually explode as supernovae, depositing a large amount of momentum and energy into the surrounding ISM. But what I want to highlight here, and you can see with these little insets, is the incredible range of scales that we're talking about here. So the scales of this large scale structure, here's a bar here on the bottom showing you 25 megaparsecs. The scale of an individual dark matter halo might be a few hundred kiloparsecs. Galaxy might be, say, 10 kiloparsecs. And this process of stellar feedback is happening on parsec scales or even subparsec scales. And similarly, then we think that massive black holes, supermassive black holes, can form in the centers of these galaxies and also eject vast amounts of momentum, radiation, and winds and jets, and have a huge effect on the surroundings. But again, the mystery is how processes happening on this very small scale, where the black hole is forming and depositing the energy, can affect these much larger scales. So this is one of the biggest open questions in galaxy formation, in my view, is how these processes occurring on small scales, subparsec scales, produce exactly the right effects on all of these global scaling relations and on the structural kiloparsec scale structure of galaxies. So we are living at a very exciting time as astrophysicists. We are expecting a large number of new and very powerful experiments will turn on over the next decade, which will survey galaxies over large areas of the sky. For example, Euclid, Nancy Grace Roman Space Telescope, the Vera Rubin Observatory, the Dark Energy Survey has already begun. SphereX is a MIDEX mission that will map emission lines using a technique called intensity mapping. The Simons Observatory is a high resolution CMB experiment. So all of these experiments will be starting to produce data over, in some cases, over the next few years and over the decade. And at the same time, we also have facilities that will allow us to study the internal structure of galaxies and other objects in incredible detail. So at very, very high resolution, including, of course, the James Webb Space Telescope that launched in December, which I'm sure we're all very excited about, but also large telescopes on the ground being built both by Europe and the United States, as well as perhaps future large radio arrays, and eventually perhaps even a very large UV optical IR telescope in space, which was recommended by the US Decadal. So let me focus for the moment on three kinds of observations that these new experiments will be producing for us. So one is measurements of galaxy clustering and weak lensing, which will come from the next generation of galaxy surveys over much, much larger areas than the Sloan Digital Sky Survey, and also reaching back to much higher redshifts. Then I also mentioned line intensity mapping, which instead of identifying individual galaxies, maps emission from a particular tracer. So in this case, what you see is ionized carbon, C2. So you just see a particular frequency range that you can then map to a line. So this emission comes from dense gas in the ISM of galaxies. And then these next generation CMB experiments, which will have very high angular resolution, will allow us to measure what are called CMB secondaries, like the thermal and kinetic Sunyaev-Zeldovich effect, which are caused by distortions of the cosmic microwave background radiation when they pass through the hot diffuse gas around groups and clusters of galaxies. So this will allow us to probe the gas around galaxies. So the world, the international community, will be spending an enormous amount of money, billions of dollars, probably tens of billions of dollars taken all together, to do these experiments. And in my view, we have a responsibility to put in the work to make sure that we can extract the maximum amount of science from these observations. And in my view, we are not ready. We do not have the right tools to really do this job well. And that's because this is an incredibly hard problem. So as you've already seen, modeling the distribution of galaxies or of gas around galaxies involves these very complex processes that are highly nonlinear and operate across a vast range of scales. Also, we need to incorporate all of these diverse kinds of observations together into the same framework. So we need to account for the observational effects for many different types of experiments. Ideally, we would like to obtain rigorous statistical constraints, so confidence intervals, for example, on the parameters in this high dimensional space. And as I've already sort of alluded to, the effects of cosmology, so for example, changing the nature of dark matter could have a degenerate effect with changing the way that astrophysics, so for example, that feedback processes work. So we need to be able to disentangle those different effects. So we've made a huge amount of progress over the last decade in producing numerical simulations that represent these physical processes that I've been talking about. So here's a very incomplete list of some of the large volume cosmological hydrodynamic simulations that have been published in the past few years. And these have taught us a lot about galaxy formation, cosmology, and large scale structure. But I want to sort of set the stage for you by showing you this diagram, which comes from Nelson et al., 2019. So this shows on the x-axis the number of galaxies that can be resolved in the simulation with a mass greater than 10 to the 9, or I kind of prefer actually the top axis, which is the volume that can be simulated. And then on the y-axis is the baryon mass resolution. And you can see that this axis is backwards, so there are smaller numbers going towards the top. So that means that as you go up, this is sort of better resolution, finer, higher resolution. And you can see all these colorful points on here showing recent simulations, both what we call sort of large box simulations, where you just simulate a large periodic volume in a box, and then up here towards the top left, what we call zoom in simulations, where you might take just one forming halo and simulate it at much higher resolution. But what I want you to notice here is that the mass and spatial resolution of the simulations that can represent, even relatively small volumes, but decently large volumes, the resolution tends to be something like, at best 10 to the 5 solar masses, and the spatial resolution is at best a few hundred parsecs. So obviously, we are not going to be able to simulate things like how supernova explosions affect the gas around them directly, right? We are not going to be able to resolve those processes. So we have to use what we call subgrid recipes to represent those processes. And just, to sort of think about what we're aiming for, right, these new experiments are going to be probing galaxy clustering and the distribution of gas over gigaparsec volumes, right? So we really need to be off the right end of the chart here in terms of what we're aiming for. So I mentioned the need for these subgrid treatments. And this is an incomplete list of the many, many processes that have to be simulated using subgrid in these simulations that I've just been showing you. This is a little bit of a depressing list, perhaps, because really we need to think hard about each of these processes. For today, I want to pick just one of them, which is stellar feedback, stellar-driven winds, and tell you about some work we've been doing to try to make those subgrid recipes more physically grounded and we think more realistic. So let me first tell you what is commonly done currently. Now there are, of course, many different ways to implement these subgrid processes, and I'm just going to sort of pick one of them as an example, but of course there are many different ways to do this. So this is what are sometimes called hydro-decoupled stellar-driven winds. So basically you launch a wind, you create a particle, and you turn off the hydrodynamic forces. So that particle, it can feel gravity, but it no longer feels the hydrodynamic forces. And so that particle gets a kick, right? It gets a velocity. Typically a fixed velocity is used that is proportional to the velocity dispersion of the dark matter halo on the scale where the wind is launched. And the number of particles that you kick, the number of wind particles that you launch, is given by this m dot out, so the mass outflow rate. And this is often expressed as something that we call the mass loading. So that's this eta wind here, and that's just m dot out divided by the star formation rate. So in the current approach, people just put a function here, and you can put whatever you want there, right? So people just put in some function, maybe it's motivated by something, maybe it's not, that has some parameters that can be tuned. Okay, so this is not necessarily very physically motivated, and it has tunable parameters. And then you look at a bunch of these scaling relations. So again, this is a very complicated plot that I won't go through in detail. Let's just pick one panel. So this is the same thing we were looking at before, the halo mass versus the fraction of the mass in stars over the mass in baryons. And you can see the gray swaths are those same sort of empirical constraints. So we're kind of aiming for that to match observations. And these different colored lines are what you get in the illustrious TNG simulations when you change various parameters in the subgrid. So these are all parameters of the stellar-driven wind model that I was just showing you. So you can make the winds faster, slower, stronger, less strong, and you can see how that changes this relationship. So you just adjust those parameters to sort of get what you want to match these global galaxy observations. And when you do this, I mentioned earlier in the talk that we struggled as a community for a long time to make galaxies that look like real galaxies. So we now can make galaxies that look a lot like real galaxies, right? So these are actually galaxies from the illustrious TNG simulations. And some of them, if you put a little noise in there and squinted at them, we might be hard pressed to tell that these are not real galaxies. And in addition, you can see that these simulations do produce, of course, the kinds of large scale structures that are seen, and they qualitatively reproduce many of those observed correlations between large and small scales. For example, the morphology density relationship, the color density relationship that I mentioned earlier, that are seen in observations. So these simulations, and again, TNG is just an example. There are works by many groups showing this level of success and agreement with both large and small scales. And if we look at how well these different simulations agree with each other, right? So as I mentioned, many different groups have done this. This plot is now a little outdated. This is from a review that I published with Ramil Dave in 2015. But this is showing the stellar mass function at different redshifts, predicted by different simulations and also by some semi-analytic modeling techniques, which I won't go into much in this talk. And you can see that for this particular quantity, for the stellar mass function, there's pretty good agreement between these different simulations, even though the codes are different, the approaches for modeling the subgrid are different, but they're sort of within a factor of few of each other. Now that is not true though for all of the predicted quantities. So here's an example, an important example of where the different simulations diverge quite significantly from one another. So this is showing the power spectrum of the matter in a simulation. If you run the full hydro simulation divided by the power spectrum you would get if you ran a dark matter only simulation. Okay, so you can think of this as showing the effect that the baryonic physics, so all of this cooling and feedback, etc., have on the power spectrum. That's obviously very, very relevant for interpreting kinds of experiments that I mentioned at the beginning of the talk. And these different colored lines show results from, again, these different large volume simulations. And you can see that those can be very, very different. And those differences are certainly much, much larger than the sort of percent precision that we need in order to constrain things like the nature of dark matter and the nature of dark energy. Obviously, if the baryons can change things by an order of magnitude, then, or even a factor of a few, then it's going to be very difficult to learn about cosmology or fundamental physics. So there's a number of things that I think we should be concerned about with the existing generation of hydrodynamic simulations, at least large volume cosmological simulations. So these subgrid models typically depend on fairly global, fairly large scale galaxy and halo properties, and they're tuned to match global observations. So of course, it's a little bit unclear always what is being predicted and what is being sort of put in, right? As we've also seen, there can be very different predictions for quantities that were not part of this calibration procedure, right? So different ways of implementing the subgrid give you different predictions, which is obviously not good. And then finally, even for the things where the different simulations might agree with each other, they might be getting the same answer for different reasons, or even where simulations are agreeing with observations, they might be agreeing for quote unquote the wrong reasons, right? So the physics might not be what's actually happening in the real universe. And it's you know, with this approach, it's very difficult to tell. So in order to address those concerns, a number of us launched a collaboration called SMAUG, which stands for Simulating Multi-Scale Astrophysics to Understand Galaxies. Greg Bryan and I are the directors, and this involved a number of institutions as well as the Flatiron Institute. And you can read more about the collaboration and see some of our papers at the website below here. So the philosophy of SMAUG is that we don't want to use these phenomenological subgrid recipes anymore. We want to instead design a set of simulations on different scales to explore how these different physical processes actually work, and then develop subgrid models that represent that physics. So we might need to use idealized simulations, we might need to use analytic models that we can embed inside of our numerical simulations. But the point is that we drill down until we can actually simulate the relevant physics, and then we build back up to the scales of galaxies and large scale structure. Now we still have parameters in our subgrid models, but we are not allowed to tune those to match observations. Instead, we can tune those, for example, to match our higher resolution simulations. And these might be dependent, in fact, they typically are dependent on the resolution of your simulation, right? So depending on the resolution, you may be able to explicitly capture more or less of the physics. And so your subgrid should be dependent on resolution. Then the validation of these simulations should not focus on just one galaxy property. So for example, the stellar mass function is very commonly used. We should look at as many different components of galaxies as possible. We should look at the cold gas in the ISM. We should look at the hot gas in the CGM. We should look at, as many things as we can possibly measure. And we should do this in the observational plane with a proper accounting for the observational errors and selection effects. So that's the SMOG manifesto. And so let me tell you about one of the core projects of SMOG, and that is a new model for stellar-driven winds in galaxies. So if we look at large-scale stellar-driven winds in real galaxies and observed galaxies, this of course is a poster child, M82, and the different colors are showing different wavelength observations. So the red, I think, is X-ray, or maybe the red is IR. Okay, I can't remember my color scale now. Yes, so the red is Spitzer, the orange is Hubble, and the blue, okay, I can't remember. Anyway, these different components are showing different temperatures and densities of gas that is outflowing in this galaxy. And what you can see is that the winds are very multi-phase, and they have gas at a broad range of temperatures, densities, and velocities. Sorry, my cursor is, there it is, okay. And similarly, if we carry out a simulation in which we can actually resolve the supernova explosions that we think are partially responsible for launching these winds, we also see that the winds are very complex and multi-phase. So this is showing you a simulation called Tigris, and you can see what it stands for here. These were developed by Yves Ostreicher and Chang-Gu Kim, and these are what we sometimes call tall box simulations. So these simulations are very high resolution. They typically have a spatial resolution of parsecs, and we can only simulate a slice of a galaxy that's around 500 parsecs across and 1.5 kiloparsecs in height. But these simulations can actually resolve the set-off-Taylor phase of the supernova explosions and allow us to study how winds are actually launched. And so you can see here, so the left panel is number, density, the middle is temperature, and the right is magnetic field. You can see the sort of blue material here that stays close to the center, and then the redder, hotter phase of the winds that escape further out. So here is a phase diagram of the winds in those high resolution Tigris simulations. So this shows on the x-axis the velocity of the winds in log space, and on the y-axis the sound speed or temperature of the outflowing material, again in log space. And so ignore the bottom panel actually for now. In the top panel is shown this mass loading factor. So this is showing, if you weight by mass, how much mass is coming out, where does the outflowing material lie in this phase diagram? So you can see that most of the mass is in this relatively cold and slow moving material. And we sort of saw that in the movie, right? That cold material didn't move very fast, kind of stayed near the center, just went around in a fountain. But then in the middle panel is an energy weighted version. So what we call the energy loading. And you can see that that's dominated by much hotter and faster material. So right away, there's a problem here with the numerical implementation that is typically used for these winds. So if you're picking a fixed mass of wind particle, then basically all your winds are going to be completely cold. You won't have any hot phase because there's so little mass in this hot phase. But the hot phase, as you could see, is energetically very, very important. So this is something we'll come back to. So these Tigris simulations, of course, they're wonderful for studying how the winds are launched, but we think that this baryon cycle, this cycle of outflows that then perhaps interact with the CGM and condense and reaccrete back onto the galaxy, that this is a critical piece of the galaxy formation puzzle to understand. And in Tigris, we can't study that full baryon cycle. We can, we're only studying a slice of the galaxy. So we can't study how the winds interact with the circumgalactic medium when they get further out from the galaxy, or how they might reaccrete back into the galaxy. And this is also a very hard problem because this cold material moving relative to the hot material, of course, you get contact instabilities like Kelvin-Helmholtz and Raleigh-Taylor instabilities. And so the cold phase can exchange mass, energy, and momentum with the hot phase through these mixing layers. And these processes are happening, again, on subparsec scale. So they are not resolved in any galaxy scale simulations. So in order to try to address both of these problems and create a complete model for multi-phase galactic winds on large scales, we've developed what we call the Arkenstone project. So if you know your Tolkien, you might remember that the dragon Smaug had a favorite treasure, which was the Arkenstone. So this has been led by Matthew Smith and Drummond Fielding, who are both postdocs with the Smaug collaboration. And the Arkenstone project has two parts. So the wind launch, so the wind mass loadings and energy loadings are taken from those resolved ISM simulations, the Tigris simulations that I showed you. And then the wind particles are launched with a velocity, temperature, and metallicity that is sampled from a distribution, again, from those Tigris simulations. And there's actually a publicly available tool called T-Wind that will produce these sampled distributions for you if you want to implement this yourself in your own simulations. So then the second piece is how the winds evolve and recouple with the surrounding gas. So for the first bit, when we launch a wind particle, remember before it had basically a fixed velocity, just one velocity. So it would have been just one point in the x-axis space here. And it probably would have just been like down here, right? Very cold with one velocity. So instead, we sample from this distribution and we use two different sets of particles. So we use much smaller mass particles to sample the hot phase in order to solve this sort of weighting problem that I mentioned before. So then Drummond Fielding and collaborators have done a large set of idealized simulations of these turbulent radiative mixing layers, right? So these interfaces between the cold and hot material, and studied how mass, momentum, and energy are transferred in these turbulent radiative mixing layers. So there's a very beautiful paper that he published in 2020 showing that these interfaces are actually fractal surfaces, which allows you to derive a number of scaling relations for these critical quantities. And then in Fielding and Bryan, they wrote down a set of equations that describe how these clouds can grow via cooling, right? So this gas can be cooling and cause the cloud to grow in mass, or the cloud can be shredded in the mixing layer and be destroyed and mixed back in to the CGM. And the fate of a particular cloud depends on its conditions as it travels outward in the CGM. So in our new model, now each of these wind particles, instead of turning off the hydro forces, each of these is treated as an ensemble of these tiny cold clouds that then obey this set of analytic equations to describe whether the cold phase grows or shrinks, and how the mass, momentum, and metals are transferred between the two phases. So we've now implemented both pieces of the model into an idealized galaxy simulation. This is a Milky Way-like galaxy. And you can see here the density, the temperature, and on the bottom here is the radial velocity and the pressure in the new model. And so the big success here is that we do simultaneously see the cold material and the hot material evolving and interacting with the CGM sort of in the ways that we had hoped. So this was a huge milestone for us to get all of these pieces incorporated into a galaxy scale simulation. The next steps now are going to be comparing this with observations of outflows in real galaxies on small scales. And also, the nice thing is that there are now several groups that are able to do simulations of a whole galaxy, certainly a dwarf galaxy, and maybe even a Milky Way galaxy, with much more explicit subgrid physics. So we can now test how well our subgrid agrees with a more explicit simulation of that physics. The explicit simulations could never ever be run for a huge cosmological volume though, right? So if our subgrid recipe is working and doing what we want, then there's no reason that we can't implement this in a large volume cosmological simulation. Okay, let me now give you a taste of some of the other work we've been doing in SMAUG. So of course, the other very important piece of this problem is how supermassive black holes form, grow, and affect their surroundings through various kinds of feedback. So this is in some ways an even harder problem than the stellar feedback, but it's one that we're very, very interested in. So one of the nice pieces of work that came out from SMAUG last year, led by Daniel Angles Alcazar in collaboration with the FIRE team, was something that Daniel calls hyper refinement simulations. So what we wanted to understand here was how gas can lose almost all of its angular momentum and accrete from these large scales of the cosmic web, the megaparsec scales of the cosmic web, into galaxy scales, and eventually all the way down onto the parsec scales of the accretion disk. So obviously this huge range of scales is not simulated in a standard cosmological simulation, even in a zoom-in simulation. So the FIRE2 standard zooms have quite high resolution because they're zooms, but they can't get quite so far down. But so what Daniel did is to run the zoom up to a point of interest. So we picked, for example, a phase of rapid accretion that might be similar to a forming quasar. And then he stops the simulation and he goes into the center and he makes all of the particles smaller. So he increases the resolution, and then we run a little bit and then we stop and we do that again. So we keep zooming in and zooming in. Here, I'll show you a movie of how this looks. Sorry, it's in light years. This was used for a public talk, I think. But you can see that as you keep zooming in, you just keep seeing these finer and finer structures. And the dynamics of these structures are critical for understanding how the gas loses angular momentum and is able to fall to smaller and smaller scales. So the little X is the black hole actually orbiting down in the center. And you can see how the black hole moves relative to the center of the potential well of the galaxy, which can also affect its accretion. And now we're zooming back out. Okay. So in these simulations, we could use direct gravitational capture to measure how much matter is actually becomes gravitationally bound on the scale of the black hole. And then we could test a commonly used subgrid recipe called the Bondi-Hoyle model that is often used in simulations to describe the accretion rate onto black holes. And what we found was that in all of the conditions that we studied, that the Bondi-Hoyle model is terrible. It overpredicts the accretion rates by up to 4 to 5 orders of magnitude. And the Bondi-Hoyle model, as many of you know, scales fairly strongly with black hole mass as the black hole mass squared. And we did not find such a strong scaling with black hole mass. So we're now doing more of these simulations and trying to build an analytic recipe describing black hole accretion that, again, can be implemented in large volume cosmological simulations. Okay, let me give you a quick taste, really just an advertisement of one other branch of SMAUG, which has really spun off into its own project and collaboration. I think it's very exciting. So this has been led by Paco Velasquez Navarro, Shai Genel, and Daniel Anglos Alcazar, who are all on the staff here at Flatiron. Daniel is jointly appointed with the University of Connecticut. And so CAMELS stands for Cosmology and Astrophysics with Machine Learning Simulations. And what we've done is to run thousands of relatively small volume, so these are only 25 megaparsecs on a side, fully hydrodynamic simulations spanning a broad range of different cosmological parameters, so range in omega matter and sigma 8, as well as changing these free parameters in the stellar feedback and the AGN feedback subgrid recipes. And we've done this using 2 different galaxy formation models, existing galaxy formation models. One is Illustris TNG, and one is the SIMBA model. So these 2 models implement the subgrid in different ways, as well as being able to tune these parameters. We've produced a huge amount of data, and all of these data are publicly available. So you can go and download these data and play with them. But so these simulations were really designed as a playground and a sandbox for developing and exploring machine learning methods for learning about astrophysics. So this is just showing you each of these teeny weeny little squares is one of the different simulations from CAMELS. And so here on the left is showing the TNG simulations, dark matter stars, gas density and temperature. And this is the same simulation with SIMBA. So you can see here that, for example, the stellar distribution looks pretty similar. Of course, the dark matter distribution looks quite similar. But for example, the gas temperature looks very different. So this is just an example of how the different subgrid implementations can lead to very different conditions in some of the components in the simulations. And what we want to be able to do is to test how robust any particular machine learning application that we might develop is to these different implementations of the subgrid physics. So here is one of the experiments that we did. So we took a neural net, a convolutional neural net, and we said, what if we knew the total matter density field? Okay, so we bin the matter density field, and let's pretend we knew that in the real universe. Of course we don't, but let's pretend we did. Can we train a neural net to learn the value of omega matter and the value of sigma 8 and or the value of sigma 8, the normalization of the power spectrum, from that information? And so basically what it's doing is it's looking over these thousands of simulations with these different parameters to try to find the best representation of the matter density field. And what we found was that actually we can constrain omega matter to an accuracy of around 3 to 4%, and sigma 8 to an accuracy of around 2 to 3%. So that was actually very interesting and encouraging. And so you can see the different colors here. For example, the blue and the green are what happens if we train on one simulation. So for example, we train on Illustris TNG, and then we test on Simba. And so the fact that we're getting similar answers when we train on one and test on another simulation to when we train and test on the same simulation is encouraging. That's telling us that the machine is able to sort of, what we say, marginalize over these uncertainties in the astrophysics. It's able to just ignore those differences and sort of hone in on the relevant things that we want it to learn. So then just the last thing I want to tell you about is another branch of CAMELS that I'm very excited about. This was done almost single-handedly by a recently minted graduate student from Arizona State University, Lucia Perez, who will be coming as a joint postdoc to CCA in Princeton next year. So she wanted to study how we could learn parameters from galaxy clustering. And the existing CAMELS volumes were just way too small. So with 25 megaparsecs, you can't really do galaxy clustering. So she ran another 1,000 dark matter only simulations that are 100 H inverse on a side. And of course, we can't run these with full hydro. So these, what you're seeing here is you're zooming through these different simulations with these different cosmological parameters, different values of omega matter and sigma 8. So this would be much too expensive to run with full hydro. So we used the Santa Cruz semi-analytic models, which we have reason to believe sort of represent the clustering properties of galaxies quite well in a similar way to these hydrodynamic simulations. And we varied the astrophysics parameters, so the supernova feedback efficiency and the AGN strength, in a similar way to what was done in the hydro version of CAMELS. So she created another 5,000 or so, or more, maybe it's 10,000 simulations. All of these data are also available online. And then she used as training data things that we can actually measure in these upcoming galaxy surveys, things like the galaxy 2-point correlation function, counts in cells, so just counting galaxies in different volumes, the void probability function, so the probability of finding no galaxies in a particular volume. And so here are her results for how well we could constrain omega matter. The root mean squared error is only around 0.028, which is quite good. And sigma 8, the constraints are less good, but still we found this very encouraging. We were also interested in whether we could constrain the values of the astrophysical parameters. So for example, the supernova feedback or the AGN feedback, and this did not work well. And again, this seems to be telling us that this, these particular data, these training data, it's not that they're not sensitive to these astrophysics parameters, because of course they do vary strongly as a function of these parameters, but the machine doesn't seem to be very sensitive to it. The machine seems to, again, sort of focus in on the cosmological parameters. So this is something we're working on, trying to design ways to make the machine learn better about the astrophysics parameters, because that's of course something that we're interested in as well. Okay, so what are the next steps? I realize I'm running actually way over where I wanted to be, but let me tell you quickly, the next steps are, we think that this forward modeling approach is really the only way to capture this complex and nonlinear physics. We need to be able to push the simulation predictions to the observational plane and add instrumental effects. But even once we've developed these new physics models, these simulations are much too expensive to simulate the thousands of times that are needed in order to do inference. Another problem with doing traditional inference, where you write down a likelihood function, is that the form of the likelihood is in general not known, and we don't expect it to be Gaussian. So let me just end by telling you about this new Simons collaboration called Learning the Universe, where we plan to continue to develop the new subgrid models using the approach pioneered by Smaug, to accelerate those simulations by orders of magnitude using machine learning, and then to develop new inference methods using implicit likelihood to place constraints on both cosmological and astrophysics parameters. So let me leave you with my summary. Actually, maybe I'll stop sharing and take your questions. Thank you for listening.
Thank you, Rachel, for this beautiful seminar, this wonderful review of the many work that you are leading and collaborating. So I think that the floor is open to questions, and so if any of the remote attendants want to ask questions, they can simply switch on their mic, or we can give word to the people here in the room. Just let me know. But I can start. So I was very impressed by this result that you were mentioning regarding the Bondi-Hoyle accretion, and so orders of magnitude seems to be somehow scaring, no? With respect to what we usually tend to believe in our modeling. My question is actually how, because I was curious to understand exactly how you run the simulation, because what you find must also depend on the way you really model the feedback of the accretion on the surrounding gas. So I was curious to know a little bit more on what kind of choices did you make to take this into account?
That is a great point, Rafaela, and I'm sorry I forgot to mention something very important, which is that we decided we wanted to just study the accretion process in isolation. And of course, you're absolutely right that the accretion and the feedback are very degenerate. They'll both have very strong effects on the accretion. So we just switched off the feedback. There was no AGN feedback. There is stellar feedback in those simulations using the FIRE model for stellar driven winds, but there is no AGN feedback. So we wanted to first, try to develop a formulation without feedback. And now we just started having meetings discussing how to include the feedback and study the case where you do also have feedback. So I don't know if you saw a recent paper by Sarah Wellens and the FIRE collaboration, where they studied these different methods of including the wind. So including like these split wind particles. So we'll be using a set of those implementations from the Wellens paper to extend this study and include the feedback. But yes, absolutely, that's what makes the problem so very difficult and complicated.
Sure, but it's also a very reasonable choice if the aim was really to test the accretion model.
Yes.
So in this case, what you find is that it's essentially a sort of effective accretion when you account also for stellar feedback, or
exactly. Yes, that's exactly right. Yeah,
a very, very nice result actually. So any question from the audience or from the remote attendants? I don't see. Yes, so it's a question from Kazuo Mukai, who is here visiting, and he's coming closer. Yeah, I think that you should closer. Okay, so to let. You can.
Thank you for very impressive results. So I was curious about the way you used machine learning in the maybe. So if I understand correctly, so that you used to constrain the parameter set of the subgrid models, but I'm curious about the machine learning can improve the the way of analytical implementation of the subgrid model, or because the sub-analytical implementation that you use some formula, but this is not unique. So can you use machine learning in that way? So do you have some idea about that?
Yes, you're absolutely right. So we have not done that in the CAMELS project. In the CAMELS project, we are using machine learning to sort of, replace the inference procedure to solve the inverse problem. But yes, as part of learning the universe, that is one of the things we want to explore, is actually having a little machine running inside the simulation and emulating the subgrid model that, for example, could be taken from one of these higher resolution simulations. So for example, instead of sampling that distribution manually the way we've done, we could have a little emulator that runs inside the simulation. So that is definitely something we're going to be exploring.
Okay, thank you.
But at the same time, it was quite impressive, the result that you found that at least in the test that you have done, I mean, it seems to be hard for the training net to recognize the analytical, the baryonic physics. So isn't this somehow scaring, or how, I mean, what is this telling us in terms of machine learning applications for really, in the perspective that Kazu was alluding to?
Well, I think these are a bit two separate issues, but I think that it depends what you ask it to learn, basically what you use as the training data. And we deliberately chose quantities that we thought would be relatively insensitive to the astrophysics, because we wanted to explore, mainly the potential for constraining cosmology. But we're now looking in, so you can pick other quantities. For example, if you pick the temperature field of the gas, that's very sensitive to, for example, the AGN feedback parameters. So it's actually nice because you can pick different quantities and ask which parameters are they the most sensitive to, right? And the machine will sort of will tell you that and give you like a ranked list of what they're the most sensitive to, and it will disentangle them, which is very difficult since, of course, they're very degenerate.
I see, right. So that's really super interesting. Any other questions or curiosities for Rachel?
If not, so can I
ask
one more? It's
Kazu
actually not very related to your today's talk, but I'm just curious about this kind of subgrid the modeling and or the sort of the semi-analytical modeling. So is there any other the field of physics not limited to the galaxy formation, this kind of subgrid modeling is very successful? Do you know that?
Oh, that's a great question. Yeah, that's a fascinating question. So of course, there are many other fields that have exactly this same kind of problem, right? This multi-scale problem. So for example, we've been talking a lot with oceanographers. They have exactly this problem. Climate modelers have this problem. People modeling cells, right? People modeling the brain. So there are many people working on exactly this problem. Interestingly, so we started reaching out to these other communities, hoping that they would have been further along and that we could learn from them and use their techniques. It turns out they're like, oh, you're doing that. That's so interesting. We need, so they're actually behind us in some ways, at least so far, the ones that we've talked to. But it is very interesting that I think, as we develop these techniques and tools, they will have very broad applicability across different domains. And I think it's very fruitful for us to have these conversations with different people from different areas. Yeah.
I didn't know at all. So thanks. Yeah, very interesting.
Yeah.
Thank you, Rachel. So you haven't mentioned that all the what are you planning to do with coming James Webb observations? So I don't know if you can give us some ideas on how all these enormous simulation and theoretical efforts will be best exploited for at least the first data release. I don't know if you have time and willing to share this with us.
I'm very happy to share as long as people are available, but of course, anyone who needs to go should feel free to go, because I'm sorry I went so long. Yes, so I think that the observations we'll be getting from James Webb will be an amazing laboratory for testing both our current subgrid physics implementations, but also for testing these new subgrid physics implementations. So for example, we've been focusing very much on low redshift conditions, like all of these tigress simulations were run for Milky Way-like conditions, but now we're extending them down to much lower metallicities, to the high densities that will be probably typical in the early universe. And I think it's so important as almost a stress test to see, you know, will things work in these very, very different conditions that we'll see in the early universe. And so the first observations from JWST, you know, even very basic things like how many galaxies do we see at redshift 10, with what masses, with what are their kinematics look like, what are their sizes look like. I think this will be a stringent test for these new models because they have been developed very much, you know, sort of with a local universe lens. So I'm very, very excited about that.
Okay, so thank you so much, Rachel, for this wonderful seminar, for sharing your time with us. And I hope to really meet you soon in person in Rome.
Thank you so much. Thank you to everyone for listening. And thank you, Raffaella, again, for inviting me. And I also hope to see you soon in person.
Okay. Goodbye. Goodbye. And
ciao.
all of you.
Bye.
Bye-bye.